Hello, my good students. This is alternative delivery for March 26th. I'd like to start off by commending you guys for being flexible. I really have enormous respect for your resilience. Like these trees that are bending with the wind, we can bend with this and we can accomplish our objectives. I'm quite confident that teaching and learning can continue unabated. Grades will be rendered and goals need not be deferred, educational goals. So please, if at all possible, stick with the program. Today's overall objective focuses on applying our techniques for finding maximum and minimum values and using the first and second derivative tests in so doing to solve applied problems, and these are also known as word problems. Like all word problems, the formulation will be the key, and that's one of the things that will require some thought as you work through these kind of problems. Let's begin with this example. We need to enclose a rectangular field with a fence. We have 500 feet of fencing material, and a building is on one side of the field, so we won't need any fencing there. Determine the dimensions of the field that will enclose the largest area. Now, it will be to your advantage to pause the video, work on this problem for a while to understand it, perhaps to solve the problem, and then come back when you are done and hit play on YouTube again. So pause now. Let's see how you did. Often in word problems, drawing a picture is useful, and you can see the picture that I have up here of the building, and I define variables x and y to be the length and width. Okay, and in fact, realize that x and y must be greater than 0 and also less than 500, because otherwise you wouldn't have a rectangle. And so those are constraints that we know of. Now, the problem then asks us to maximize the area, and the area of this rectangle is going to be x times y. And the constraint that we have that figures into this problem is that you only have 500 feet of fence. So we have y and x must add up to 500. And that means we can solve for x in terms of y and get x is 500 minus 2y. So if we substitute this into the area function, we'll find out that we now have a single variable, y, and so the area as a function of y is going to be this product, which could be simplified this way, and it's probably easier when you simplify it this way to take the derivative. So recall the maximum value of a continuous function, which we indeed do have here. It's a parabola on a closed interval, which we also have here, will occur at the critical points or the endpoints. And we've already pointed out the endpoints give you 0 areas, so they don't make any sense. This means our only option will be the critical points. So what we do is we find the critical points. We take the first derivative. A prime of y is 500 minus 4y. Set this to 0 and solve. And whenever we set that equal to 0 and solve, we get y is 125. Now, if we plug this into the area equation itself, either this one or this one down here, we'll find that it is 31,250 square feet. So according to the method from the extreme value section we covered previously, this must be the maximum possible area, since the area at either endpoint is 0. Or, more recently, we have studied the second derivative test and note that a double prime is equal to minus 4, which is less than 0. So this is indeed a maximum by the second derivative test. We're going to do a more complicated example now, and this is from the business world. The first problem was a maximization problem. This will be a minimization problem. So how you do inventory management is very important in business. It can be a determining factor for businesses succeeding or failing. And here is conceptually what is going on. There are two fundamental costs associated with inventory. One of them is going to be the ordering cost. How frequently you order determines your ordering cost. If you only order once, you just do it once. If you order many times, the cost is higher. But then you have a conflicting objective, and that's your carrying cost. If you only order once, you have to carry the cost of this inventory for a longer period of time. So there's a trade-off, and in fact we're interested in what happens with the total cost, which is the sum of these two. And if you look at this picture for a while, you see, oh, it looks like there's going to be a sweet spot here. We're going to use calculus to find that sweet spot. The technique introduced here is sometimes called Wilson's EOQ model. EOQ stands for economic order quantity. We're going to be looking at what is the amount that we order each time. Although the assumptions in this model are quite idealized, this model is used today, and many embellishments have been made since as well by industrial engineers, and this is incorporated into many manufacturing management software products as well. So here we go with the formulation. The economic order quantity model applies only when the demand for a product is constant over the year. That almost never happens, but that's the assumption. And each new order is delivered in full when the inventory reaches zero. The world also doesn't really work exactly that way either, but that's the model assumption. There is a fixed cost for each order placed, regardless of the number of units ordered. There's also a cost for each unit held in storage, commonly known as the holding cost. This can be insurance, it can be warehouse space, so on and so forth. We want to determine the optimal number of units to order so that we can minimize the total cost associated with this purchase, delivery, and storage of the product. So we're going to define a number of variables here. You may want to jot these variables down so the subsequent slides make a lot of sense. The required parameters are the total demand for the year, which is called, let's see, D. The purchase cost for each item, and the purchase cost for each item is going to be P. The fixed cost to place the order and the storage costs per year, those are going to be the holding costs, and that's going to be H is the holding cost down here. And let's see, the order cost also is K. I don't guess I didn't talk about it up there, but that is the cost of ordering, shipping, and handling. This is not the cost of goods. And we're going to let Q be the variable that we're going to order, and we're going to then seek to find Q star, the optimal order quantity. Note that the number of times an order is placed will also affect the cost, but this number can be determined from other parameters. I'll say more about that later very soon. So the total cost of and derivation of the economic order quantity formula. So the single item EOQ formula finds the minimum point of the following cost curve. So the total cost is going to be the purchase cost, the ordering cost, and the holding cost, three components. The purchase cost, this is the variable cost of goods. That is the purchase unit price times the annual demand quantity. This is P times D, and P times D sits right here. Now we have to have the ordering cost. Now each time you order, it's going to involve a cost of K, but you have to figure out how many times you have to order. Now this really is going to be D over Q, and let's discuss why that is true. Pretend that your demand over a year was 2,000 units, and you were going to order 500 units at a time. You would be ordering 4 times, because 2,000 divided by 500 is 4. So that logic tells you that the number of times you order is D over Q. Then we also have a component for the holding costs. So here we have the ordering cost, D over Q times we order times K, and the holding cost is the average quantity in stock. And you see, if you're replenishing between being full and empty, the average amount is Q over 2. So this cost is going to be H times Q over 2. So we've explained this equation. Now, to determine the minimum point on the total cost curve, and think about that, the variable here is Q, how many we order at a time, we calculate the derivative of the total cost with respect to Q. And all other variables are constant, and we're going to set this equal to 0. Now, when we take the derivative of this, P times D, there is no Q, so the derivative is going to be 0. This is KD times Q to the minus 1. So the derivative of this term is going to be minus KD over Q squared. And this is just H over 2 times Q, so the derivative is going to be H over 2. We set that equal to 0 as we have done before to find the critical values. So we can solve this for Q, and we get, and this is going to end up being the optimal value. So this is Q squared, the critical number, is going to be 2 dk over H. And therefore, the economic order quantity is the square root of 2 dk over H. And note that Q star is independent of P. It's a function of K, D, and H only. That surprises some students, but you're paying for these units regardless of when you get them. Now, I do want to note that, and looking back to our discussion of the second derivative rule, that if we take the second derivative of T with respect to Q, we're going to get 2 dq over Q cubed, but since Q is positive for any value, and in particular for the Q star, that's going to be greater than 0, and that means that this is a minimum, and that means we can find the minimum cost by plugging this value, Q star, into the total cost equation, and that provides us the total minimum cost. Neat, huh? Let's look at another minimization problem. This one I am going to ask you to work on. Here's the problem. I want the rectangular block containing text to measure 60 square inches. So this stuff in here measures 60 square inches. And I insist that the left and right margins are as shown, 1 inch here and 1 inch here and 1.5 inch up here and 1.5 inch here. What are the dimensions for the minimum page size? Now, the minimum page size is the entire poster, not just the text, I can use to print my book while still conforming to my specifications. So press pause, ponder the problem for a while, perhaps solve the problem, then come back and we'll see how you did. Let's see how you did. So if I set W equal to the text width and L equal to the text length, then the product of W times L has to be 60 by the constraints of the problem. The little picture is left down here for us to refer to as we needed. And that means that L is equal to 60 over W. I solve this. I'm turning a problem that has two variables into a problem that has one variable, so we can use single variable calculus. Since I am minimizing the dimensions of the page, not the text, I want to maximize the equation. And so this is going to be the size. It's going to be D of the whole page is going to be W plus 2 times L plus 3 to account for the margins. And that's accounting for the margins. Now we're going to use the substitution that we came up with up here for L. We will plug it in, and we do some algebra, and we get this resulting expression for D. We'll take the derivative with respect to W in this case, and we're going to set that equal to 0. So the derivative with respect to W is this expression, and we're going to set that equal to 0 to find the critical points. So if we set that equal to 0, we will find that W has to be 2 times the square root of 10. So therefore, the page width should be 2 the square root of 10 plus 2, because that was the width that we have. Now, to ensure that it's a minimum, we could either use the first derivative test or the second derivative test. And note that the second derivative of this is going to be 240 over W cubed. And since our value is positive, that means that that will also be positive. So this is going to be a relative minimum because it's a positive second derivative. To finish the problem, you need to find the length that corresponds to that. So we go back to our equation expressing the length in terms of the width, substitute in, and we get that the answer is, for the page length, is 30 over the square root of 10 plus 3. Some of my students would say that's the ugliest number they've ever seen in their life, but there are no ugly numbers, just like there are no ugly babies. Let's look at another more complicated example. So a piece of pipe is being carried down a hall that is 10 feet wide. At the end of the hall, there's a right angle turn, and the hallway narrows down to 8 feet. What is the longest pipe that can be carried, always keeping it horizontal, that can be carried around the turn in the hallway? And so that's going to be the problem. This reminds me of a story from math history where a great mathematician and his wife were arguing, trying to get a couch into the front door. In disgust, the mathematician went to his study and wrote a mathematical proof that the couch could not fit through the door. He went back to show his wife, but she was exhausted, but she was sitting on the couch inside the room. She had gotten in there herself. There are lessons there, I think, about life, I guess. Okay, so please hit pause, work on the problem. After you solve the problem or perhaps get stumped, come back and we'll talk about the problem together. The largest pipe that can go around the turn will do so when in the position shown above. And notice I'm breaking into two parts, L1 and L2. That's part of the cleverness of this problem. One end will be touching the outer wall of the hallway at A and C, and the pipe will touch the inner corner at B. And we're splitting it into components that we're going to call L1, which is the length of the pipe in the small hallway, and L2, which is the length of the pipe in the large hallway. So the length of the pipe then has a length of L equals L1 plus L2. Now we're going to introduce an angle, because this angle plays a key role. If theta was equal to 0, then the pipe is completely in the wider hallway. And we can see that as theta tends to 0, the point A will move down the vertical wall, and the point C will move along the horizontal wall closer and closer to the corner. And as this happens, L lengthens. So L will tend to infinity as theta tends to 0. Likewise, if theta equals pi over 2, the pipe is completely in the narrow hallway, and as theta tends to pi over 2, we're going to have L tending to infinity by similar line of reasoning as above for theta tending to 0. So, because L tends to infinity as we near the ends of the interval of possible lengths somewhere in the internal of the, inside the interval, the endpoints make no sense. We're looking for theta to be an angle that will minimize L, subject to these constraints. And oddly enough, that's the value we're after. So you see we're minimizing the length of L, but that will be the longest pipe that will go around the corner. So the largest pipe that will fit around the turn will in fact be the minimum value of L. You want to think about that for a bit. Okay, so the constraint on the problem was maybe not so obvious, and in fact there are two constraints. They're going to be the widths of the hallway, and so we use this to get an expression for L in terms of theta, and then we'll minimize this new equation. So from right triangle trigonometry, we can see that L1 is equal to 8 times the secant of theta, where we define theta, and L2 is going to be equal to 10 times the cosecant of theta, and that means L is the summation of L1 and L2, so it's going to be adding the two. So this is the thing we're going to take the derivative of. So if we take the derivative, and yes, it is important to remember how to differentiate trig functions, we get L prime is equal to 8 secant theta tan theta minus 10 cosecant theta cotangent theta. We're going to set this equal to 0, and we set it equal to 0. We add this 10 cosecant theta cotangent theta to both sides, and we get this this expression. I can reduce 10 over 8 to be 5 over 4, and the resulting expression over here will simplify because sine theta over cosine theta is also the tangent theta. So this is the tangent cube theta is equal to 1.25. And we can solve that for theta, and so the tangent of theta is equal to the cube root of the square root of 1.25, which means that theta, our angle, has to be the inverse tangent, or the arctangent, of the cube root of 1.25. And now I'm going to let us be a little bit of engineers. We're going to plug that into our calculator to find out what it is in terms of the angle, and this is in radians, of course. Okay, so if we use that value for radians, then we have a minimum length, and it will just fit around the turn. Anything larger will not fit, so the largest pipe that can be carried around the turn is L is equal to, substituting those values in, 25.4033 feet. And again, we did engineering approximations there. Now, as you know, the best way to get good at word problems is to do several. As always, I suggest you do every other odd problem in this section. That's section 4.6 in your textbook. See you in the next video. Take care.